Well, hi. So now, what I want to talk about is I want to talk about how to connect this graph to those statistics. That's what I want to talk about, because that really is the big picture. How do these numbers attach to that graph right there? Now, you guys have already done a wonderful job of identifying where the center is, or where the balance point is. 14.7, negative 14.7 is just about negative 15. So here is x bar. Here is x bar. Where is the S? Where is the S on that graph? And this is a very difficult question to answer. Where is S? Give me some ideas as to where S is. Give me some ideas.
Between positive 10 and 20.
20, what are you thinking?
Well, it's 16.4 from your negative 14.7 either direction.
So, good. So, if you go by the definition of what standard deviation is, it's an average distance from x bar, yes? It's an average distance from x bar. So what Tony just said, I love this, is take x bar, and if I go out 16.4 and down 16.4, let's see where that would put us. That would take us out to about here, yes?
Yeah.
So that would be x bar plus s, yes? If I go out that far. What would that numerically be if I add 16.4 to that? 1.7? Did I do that right? 16.4 minus 14.7, is it 1.7? I think that's right. Check my math on that one. I think that's right. Check my math. Always check my math. I kind of suck at it. Okay, I'm okay with the stat, terrible with the math. And then if I go down, is everybody okay with how I'm writing this? X bar minus S, X bar plus S? Can you live with that, how I'm writing that? Hopefully you can. So X bar minus X, X bar plus S. So X bar minus S would be 14.7 away. That's going to be a 1, carry the 1. Negative 31.1. Check my math on that one too.
Yes.
Thank you, friends. That range of values right there, let me draw this better. That range of values right there is called one standard deviation from average. One standard deviation. And a lot of times it's just called one standard deviation. Very often, if you're being very exact, you'll put from average, from x bar. That's what that distance is called. So negative 31.1 to positive 1.7 would be termed one standard deviation from average. 0.1 pounds to positive 1.7 pounds is one standard deviation. I have to apologize for all statisticians everywhere. So tight. I have to apologize for all statisticians everywhere. I hate the fact that the S is called the standard deviation, the sample standard deviation, S, the sample standard deviation, and yet this whole range of values that we've tracked out by going from negative 31.1 to 1.7 is called one standard deviation. I wish they would have called this something different, because then it might get confused. Am I talking about the number S, or am I talking about the range of values S? So just get used to it. We'll have no shortage of opportunity to get used to it as we go through this course. So good. Why? Because so tight. Why do we care about one standard deviation? Anybody have any idea right now why you care about one standard deviation?
Get rid of the outliers.
Oh, what's an outlier?
Let's say the 58 or 21.
Oh, but what, aren't we getting rid of other stuff too, though? Are we getting rid of, this is a great, you hear, tell me them again. Zach, you hear what Zach said? He's like, one standard deviation truncates the outliers off. So if it truncates the outlier, what's it leaving behind, Zach?
So the middle average.
Oh, it's leaving behind the middle. Oh, I like that. Because how did you guys describe this data when we first put it up on the screen? I said describe it, and one of the first things you said was it's bell-shaped, right? One of the first things you guys said was it's bell-shaped. That's kind of slick. It's bell-shaped. So if we focus on the high points of the bell, that's where like most of the data is. Good. Very good. So Zach said by slapping up these markers, I'm going to make it go up a little bit higher if it's okay with you guys. By trimming off anything outside of these markers, we've cut off, if you will, the outliers. Well, that's good. I like that very
Now
much.
it's kind of skewed though if you do that.
How's it skewed?
10, It's on the left, 10, 7, 4.
Oh, now you gotta remember, when you guys called this bell-shaped, you didn't mean perfectly bell-shaped. You meant bell-shaped enough. So it stands to reason you're gonna have a little bit more on one side than the other, yes? Is that what you're saying, Zach? And I have no argument with that whatsoever. Now, what you've said is 100% correct, but most statisticians don't use one standard deviation to trim off outliers, they actually use two. They go out two. Some of you may have learned this in your psych classes or your social classes. 2 standard deviations is a very, very common measure. We're going to come back to that momentarily. I want to come back to that momentarily. If you go out 2 standard deviations, so we have to go, what, 16.4 more pounds up from this, which would take us out to, make sure I'm doing this right, 18.1. Check my math on that, friends. 18.1. And then if I go 16.4 more down, that should come out to something 0.5. 50, negative 50.5? I know, thrilling. This range of values right there starts at x bar minus 2 s's and goes up to x bar plus 2 s's. Notice x bar is still in the middle of it. X bar is still in the middle of it. Now, Zach, this does trim off what are called, technically speaking, outliers. Anything outside of 2 standard deviations becomes a more formal definition of an outlier in bell-shaped data. So now we have negative 50.5 up to 18.1, and this would be called 2 standard deviations. Can we go out more standard deviations? Of course we can. We can go out 3, we can go out 4. Anybody heard of 6 sigma? Something called 6 sigma? That's 6 standard deviations. That's the same idea, but 6 standard deviations. It's amazing. It seems ridiculous to go out 6 standard deviations in this case, because you'd be going out 100 pounds essentially in either direction. But usually those things are applied to very, very precise measurements, and it's not that far on average. So you can also go out fractions of standard deviations. You can go out half a standard deviation. So in other words, instead of going out the full 16.4 pounds, you can go out 8.2 pounds. That would be a half of a standard deviation up and down. But Tony, what you said about adding and subtracting, that's the key. But now the question I have is, okay, so now we've done that, right? We've gone out these numbers of standard deviations. Why do we care about it? Like, what does that tell us? We've gone out 1 standard deviation, yes? What's in there? Now, Zach had a vote. He said, what did you say? You said it very well. What was within 1 standard deviation? I said, what did you trap in the middle there? And you said, the middle average. I have a question for everybody here. You have the raw data, yes? You have the raw data in front of you. How many of these data points are between negative 34.1 pounds and positive 1.7 pounds? Go ahead and count that up for me. How many of them? How many of the data points in that block of 35? How many are between negative 34.1 and positive 1.7? Just go ahead and do a quick count for me.
31. It kind of looks like a 4. But
oh, it's 31.1. Thank you. Oh, because I drew the damn dotted line through it. Thank you. Sorry. Thank you, Tony. Negative 31.1. I drew the dotted line in the middle of the 4. Good call on that one, sir. So between negative 31.1 and positive 1.7, how many data points? Now you're beginning to see the prerequisite quiz and why I asked you the questions I asked you on that damn prerequisite quiz. Orange marker, here you are. Number of data points within. We got a vote? 24? 24? Now, how many data points total are there in the data set? 35. 24 out of that 35 is approximately what percentage? 69%. 69%. Good. We're going to come back to that momentarily. Hold that number in the back of your mind, and really far in the back of your mind right now, because it shouldn't mean anything to you right now. Now, do the same thing, but do the same thing for two standard deviations. How many data points are between negative 50.5 pounds and 18.1 pounds? So clearly, you have the original 24 are still in there, yes? I mean, clearly they're still in there, because if they're within 1, they're within 2. But you picked up some more. I want to know how many are now within the whole shebang.
33.
We'll vote for 33? 32? 33? Want to go with 32.67 to take the average? Keep counting. Let's get consensus. Let's get consensus. I have 2 33s and a 32. Tony says, be brave.
It's 34.
34! I love this. You know what I'm going to do? I got an idea. Since you guys are all saying very large numbers, let's look at the ones that aren't in that range. So 21 is, I heard somebody say there's a 21. There is a 21, so throw that one out, yes?
Negative 58.
And negative 58 is too small to be in that range. There's 2, throw those out.
That's it.
What's the next lowest, what's the next smaller positive after 21? 16. 16's in there. Did somebody say 15? No, there's a 6. I think it's just 2 are out, so the rest are in, yes? So does everybody follow me on that one? 33 are in. So that means we got 33 in. If we convert, if Sean writes what he says, 33 are in. 34. If we convert that to a percentage, I get 33 out of 35. That's like what, like 95, 94%?
Yeah.
95? Is around the 95?
94.
Around 94? Cool. The reason I bring this up is because these percentages are going to be very, very commonplace in statistics. When your data is bell-shaped, there are certain predictable percentages that are always going to happen based on the bell-shapedness of the data. For example, within 1 standard deviation, you're going to have roughly that percent. I think the rule of thumb is 68%, I think, is the number that's often used. 68% of data is going to be within 1 standard deviation. 95% is within 2. And the reason I bring this up only is because the awesome note about throwing the outliers out, if you call this normal, 68%, that's like 2/3. You're throwing away 1/3 of your data as outliers. That's a lot. That's a lot of data going by the wayside as too big and too small. So statisticians generally, by consensus, call 2 standard deviations the outlier cutoff, because that throws away only 5% of the data as outliers. And I say throws away, I don't mean throw away in the literal sense of putting it in the trash can. We're going to deal with outliers in this class too. But identifying something as outlier data. For example, Jared, Subway. I love talking about Jared and Subway. Why are we talking about Jared and Subway? Well, he lost the most weight eating Subway sandwiches, yes? Why do they talk about me? I lost about 5 pounds over 5 years eating occasionally Subway sandwiches. Why am I not in there too, like Jared? Because I didn't lose as much weight as he did. But I would have been termed an outlier in this range, but not in this range. You see what I'm saying? I wasn't considered outlierish enough. You can't, the definition of an outlier, we'll come back to this, is data that is too extreme to be considered average. Well, if you're throwing away 1 out of 3 data points, it's almost like more than almost half of your data is considered unusual. That negates the definition of unusual. Does that make sense? Maybe not. Maybe it's Tuesday, it's still kind of early in the morning for that. This is generally, let's wrap all this up. Let's go to the sideboard. Sorry, I think I just freaked everybody out and I apologize. Maybe it was the dance, the little Jared dance I just did. That probably pushed you over the edge. I apologize for that.